Hello everyone. In this series of videos we're going to be looking at linear momentum, and we're going to start off with just a brief introduction of what momentum is and how to work with it. And what we're trying to figure out in this video is what is momentum and how can impulse change an object's momentum. So the quick definition of linear momentum is it's just a measure of how hard it is to stop or turn a moving object. So momentum as a vector is equal to mass times velocity for a single particle, or for a system of particles, we simply add up the sum of the individual momenta. And before we do our example problem, it's worth saying that Newton actually wrote his second law of motion with momentum in mind. And he said that momentum was basically inertia in motion. And this kind of makes sense because we have mass, we have velocity, so that's inertia, and it's moving. Okay, so how fast must an electron move to have the same momentum as a proton moving at 300 meters per second? Well, let's not get too much into the details here, but let's just make note of the fact that the mass of the electron is about 1,800 times less than the mass of the proton. So we want the momentum of the electron to be equal to the momentum of the proton. So mass of electron, speed of electron, is equal to mass of proton, speed of proton. So we have 1 over 1,800 mass of proton times v equals mass of proton times 300 meters per second. Mass of proton cancels, which is why I did it this way. So you have basically 1,800 times 300, which is going to be 54, and 4 zeros after it, so I think that's right, about 540,000 meters per second. Okay, here's another one. A 90 kilogram tackle runs north at 5 meters per second, and a 75 kilogram quarterback runs east at 8 meters per second. What is the momentum of the system of football players? So we want the momentum of the system. Okay, now a rookie, football, mistake would be to just take 75 times 8 plus 90 times 5. But you can't do that because momentum is a vector. So instead, what we have here is we have 75 times 8 I hat plus 90 times 5 j hat. And so 75 times 8 is going to be 600 I hat, and that'll be 450 j hat. And units for that will be kilograms meters per second. And if you want, you can write out the two legs of that triangle and try to find the hypotenuse. I'm not going to do that now, but that would be the total momentum. Okay? And you could take to find the magnitude, you could do 450 squared plus 600 squared. And to find the angle, you could say the tangent of the angle is 3/4, 450 over 600. But I would be fine with it if you just wrote momentum as 600 I hat plus 450 j hat. Okay, and so that brings us to impulse. Impulse, simply stated, is the integral of a force over a time period. So remember that last unit we talked about work was the integral of a force over a distance. Well, impulse is a vector because it's the integral of a vector with respect to time. Work is not a vector because it was the integral of a dot product, which got rid of the vector. We don't have that with impulse. Impulse, we're just integrating force over time, and time isn't a vector. And we can say that the change in momentum of a particle is equal to the impulse acting on it, or delta P is equal to J. Now this comes back to the original definition of Newton's second law. If we examine F equals ma, and if we rewrite A as dv dt, okay? Well, we bring that up to here, and on one side we can write this as f dt, and on the other side we can write it as m dv. And so on this side we have f dt, but on the right side m dv could be dp, where dp is the change in momentum. Now technically dp is dmv, so it's actually a chain rule. It's v dm plus m dv. But at least for right now, we're assuming that dm is 0, that the mass of the system isn't changing, so that means that it's just mdv. Okay? Finally, this brings us to the fact that if dp is f dt, we can integrate each side to get the total change in momentum is equal to the integral of f dt, or the impulse. And that's called the impulse momentum theorem, and that's a pretty important one to think about. Okay, so we just did this, restate Newton's second law in terms of impulse. We'll just kind of redo this real quick. Okay, so this is going to be m dv dt. So f dt is equal to m dv. And we're going to say again that this is dp, and this is f dt. So we integrate both sides, and impulse is equal to change in momentum. Okay, now one thing to point out is that usually these forces involved in an impulse are high magnitude and short duration. It's the reason why we wear seat belts, why we have airbags, because what we want to do is we want to take that force and we want to smear it out over a longer period of time. Okay, so that the total area is the same, but we have a smaller maximum for this force. Okay? So let's do a quick example. 150-gram baseball moving at 40 meters per second at 15 degrees below the horizontal is struck by a bat. It leaves the bat at 55 meters per second at 35 degrees above the horizontal. So what is the impulse exerted by the bat on the ball? Okay, so this is going to get a little bit complicated, but basically what we're going to have here is that the impulse is going to be equal to the change in momentum, which will be momentum final minus momentum initial. Now we might as well write this out. Okay, so here's the baseball moving at 40 meters per second, 15 degrees below the horizontal. So momentum initial could be written as 40 cosine 15 I hat minus 40 sine 15 j hat. And then it's going to leave the bat, so this is the initial state. It's going to leave the bat at 55 meters per second, 35 degrees above the horizontal. So final could be written as 55 cosine of 35 I hat plus 55 sine of 35 j hat. So that means that the impulse, which is equal to the change in momentum, is going to be, okay, let's look at our I hat first. 55 cosine of 35 minus 40 cosine of 15 I hat minus, well, let's do plus. Okay? 55 sine of 35 minus a negative 40 sine of 15. So we have to take that negative sign into account there, and that's j hat. Okay? Then, and this is the important part, those are just velocities, so we have to make sure that we're multiplying this by the mass. So, sorry about that, but you gotta remember to keep that mass in there. Okay, and that's going to get us a change in momentum And we'll go ahead and calculate this very quickly. Okay, and so the change in momentum is going to be 0.962 I hat, and we'll do the j hat very quickly. And that's going to be plus 6.28 j hat. And so that means that the total magnitude of this change in momentum is going to be 6.36. And you can write this as kilogram meters per second. So if the collision took 2.3 milliseconds, what's the average force? Well, F delta T is equal to M delta V, or delta P. Okay, so the force is the change in momentum. And by the way, you could also write kilograms meters per second as newtons times seconds, right? Force times time. Divide that by 2.3 times 10 to the minus 3 seconds. And you get a force of about 2,800 newtons or so. And that's just the magnitude. If you wanted the actual direction of the force, you would have to do I and j hat components. So we're not going to do that right now. Okay, and one more example. Whoops. We have an 85 kilogram lumberjack that stands on one end of a floating 400 kilogram log that's at rest relative to the shore of a lake. So there's the shore. I can't draw. There's the shore. If the lumberjack jogs to the other end at 2.5 meters per second relative to the shore, what happens to the log while he is moving? So here's the lumberjack, and he's going to move this way. Now you might have experienced this, but if you're in a boat and you run from one side to the other, the boat actually will move underneath you. And that's because essentially F equals delta P delta T. So this is a preview of what we're going to be talking about next time. But this force is actually the net force that's acting on the system. And if you're just running to the other side, there's no net force acting on the system. So there's no real change in momentum. So the momentum of the system before you ran will be equal to the momentum afterwards. So that means that even though you're running, you're 85 kilograms, and you're moving at 2.5 meters per second, that means that the log is going to have to go the other way. So 85 times 2.5 is going to have to equal 400 times v log. And then you can just solve that for the velocity of the log. And so just 85 times 2.5 divided by 400 means that it's going to be going about 0.53 meters per second to the left. Okay, so we're going to stop here, and then next time we will talk about conservation of momentum in a little bit more detail.